All right. So does anybody have any questions before we start with anything new? Anything that we're going over, something you've been working on that you've been confused about that you want some help with, anything like that? Chat window is missing. There we go. More synthesis plans. All right, you got it. By special request, let's do some more synthesis plans. We're done, and then we will look at them together. All right, so here's one. Give that one a try, and then also give this one a try. One thing that I think we're really missing from not meeting in person is I'm not getting to see your synthesis plans, like what you've come up with. So I get a little bit worried that one, somebody's coming up with something that they think is wrong, but it's actually fine because I don't actually get to see it. And two, that you might be coming up with something that you think is working and it's not working for a reason that we should talk about. So if there's any way for you to either describe your plan to me or show me either on video or by sharing your screen, it would be really nice if I could see those. Also, beyond that, if you're writing these things down on a piece of paper or a notebook or something, if you could send them to me by email, not for grading or whatever, but I'd like to look over them so that when we come back together, I can say, okay, I've been seeing these misconceptions. Because I'm guessing I will see those on the quiz and we'll talk about those, but it would be great if we could see those before the quiz so that I could help correct some of those things. So if you could take a couple minutes to work on these, and then if you're willing to describe what you've done or somehow show what you've done, either in the chat or by voice or by turning on your camera and putting your paper in front of it or whatever, that might be really helpful. If you don't want to do that, I'm not going to force you. But if we were doing this in class, you would be this, and I would be kind of walking around and taking a look at what everybody's doing, and not necessarily calling you out specifically, but at least saying, "Hey, I noticed some people have been doing this thing, and this doesn't quite work, and here's why." So if we can approximate that, I think that might be helpful. But give these couple a try and see what you can do. All right, so question for the second one, do you have to work backwards? I mean, it's always a good idea to work backwards in these. You don't have to. You never have to. If if it's just a couple steps or it's like something you've seen before, you might look at that and say, "Oh yeah, I totally know this. I can work forwards and just do this. I know exactly the steps." But if you don't know the steps, if you don't know how you're going to do it, it's more effective and efficient if you can work backwards because you know the destination you need to get to. You know how to get there. So um, there's fewer possible paths going backwards than going forwards. If you can see it going forwards, just it's fine as long as it all works. So I wouldn't say you have to work backwards, but it's generally a good idea so that you can see what's happening. All right, everybody get a chance to try these yet, or need some more time? Confused about the first one? Okay. Second one struggling on. Okay. Take another couple minutes to struggle with it. At least try to get something down. Like imagine this were an exam question or something, and you had to get something, and you were trying to get partial credit or whatever. What would you put down that was something? All right, let's take a look at some ideas here. So for the first one, so we need to make this thing from this thing. And as usual, we're going to start from the end. So we're going to look at this first and say, how can we, or what can we make this from? What's a thing that we would make this from? And to me, the key here is in the sulfur. We haven't really learned a lot of reactions specifically with making, this would be a thioether, like an ether, but where sulfur is in there. There's really only one class of reactions, we talked about this on Monday, where we can put in these sulfur compounds, and that's substitution reactions. We know sulfur is a good nucleophile, so we can think of this as doing some sort of substitution reaction as a way to form this compound. So what might that look like? Well, what that might look like is, we have something like this where X is a halogen, some kind of leaving group. And then we're going to add to that this sulfur nucleophile. And what form you put that nucleophile in, it's kind of up to you. Experimentally, we'd have to just try it and like see what worked, but maybe that's something like this. Maybe that's not a strong enough nucleophile, and instead we want to use the salt, the conjugate base, something like that. Those would both be fine ways to do that. But somehow we will looks like this, because when we look at this compound, we think, all right, well, we got to put that sulfur onto something here, and we might as well take all of this with us. Later, we might get into some more limits where I say, like, you can't use any reagents with more than 3 carbons or something. But for now, if there's no specific limits or rules or whatever, anything that works, that could potentially work, is a potential choice. So we can take this whole thing, think of that as a nucleophile, and we're going to replace some leaving group. All right, so what do we want for our leaving group? Well, so now we start looking backwards from here and say, well, whatever we have for our leaving group, we have to make it from cyclohexanol. So we want to turn, we know OH is not a good leaving group, so we need to turn that into a leaving group, replace so that we can do the substitution reaction. So there's a couple choices there as well. We can look back at some of the reactions of alcohols. How do we turn alcohols into halides? One is using thionyl chloride to make it into a chlorine. That generally works pretty well, and that's probably my first choice if I'm looking at that. If I forget about that reaction, because that was just sort of a little thing that we threw in there in chapter 8, maybe I forget about that, or maybe I forgot about that. So another way we can do it is something like HBr, which would then put a Br here instead of a Cl. This reaction is just a little bit, as thinking about it experimentally, which is not something you would necessarily do, this is a little bit messier and this is a little bit easier to use. But either on paper, in terms of a solution to this problem, either one of those is okay. So any questions about that, or does anybody have other things that they tried that we can talk about whether or not they would work? So confused about what kind of a nucleophile you could use here? Yeah. That's okay. I think what we often forget here is that we are just doing this on paper. We're not concerned with, finding a reagent that's small or cheap or whatever. So whatever you can kind of come up with can be that seems like it could exist as a molecule is probably fine, as long as it fits what we've been doing, as long as it has an analog in something else that we've been doing. We've certainly seen lots of alkyl sulfide nucleophiles in chapter whatever, the last chapter, chapter 7. So any kind of thing that you could stick onto sulfur can probably work as a nucleophile here. Did you get the first part of needing to turn the alcohol into some sort of a leaving group? Okay, so SH, let's look at that. That would also work. It would take a couple more steps. So I think that's a good idea. But let's look at that reaction. Use a different color so we don't confuse ourselves here. So let's say you turn this into something like that, and then you want to react that with something like NaSH. So what do you get? Okay, you get that, right? So that works, because then you could say, all right, we're gonna take half of this, turn it into this, and then basically react these two things together. That's another way of doing that, right? Because now this, what you've made with NaSH, is our nucleophile. So you can then use that to react with more of this and put it together like that. So that would also work if you did that. Oh, my head's in the way. Sorry. Yeah. So wait, actually, let me just move it up a little bit. There we go. Okay. So do you see what I mean here? So you're making the nucleophile that you then have to react with actually more of this to put those two rings together. But that works too. For our purposes, for these problems, eventually I'll maybe give you some more specific direction, like you have to do this in 2 steps, or you have to do this in 3 steps, or whatever. But as long as you get something at this point, as long as you get something that works, even if it takes multiple steps, that's fine. So that would also work. Questions or ideas on that one? Okay, let's look at the second one then. All right, so here, again, looking at the product, our key here, our clue, is that we are forming an epoxide. There's not a lot of choice there. We've learned that epoxides come from alkenes. Okay. So knowing that we need to make this from an alkene tells us what we need to do. And when you're first looking at a problem like this, and if you don't have your book or your notes out or whatever, it's fine to just do this without specifying the reagents, to just know, I know epoxides come from alkenes. I don't remember what the reagent is, but something like that. Especially now in our online format, you don't really have to memorize stuff because you're always going to have your book or your notes with you when you're working on these things. So as long as you remember, I can make epoxides from alkenes and kind of set up this plan, you can always look up the reagent later if you don't know it off the top of your head. By the way, even in the in-person format, as we get toward the third exam and the final, I would often give a take-home portion of the exam with these syntheses, with these synthesis problems, because I do think it takes a little bit more time to think about than what you might do under the pressure of a timed exam. So in that sense, where you could look up the reagents, that's totally what we would be doing in class anyway. All right, so we make epoxides from an alkene, and then we say, okay, well, what do we make alkenes from that could maybe get us back to here? And also, that's dehydration. So if we dehydrate, we lose OH and H, and we make the alkene. So now we can fill in those reagents. Dehydration requires concentrated acid and heat. Sometimes we write it concentrated with a specific acid. Sometimes we write H3O+. That's okay. One thing, I think this is a question on the quiz, that there's a well, we talked about it in class also, but dehydration and hydration are the reverse reactions of each other. So it's important when you're dehydrating that you're taking the water out or using as little water as possible, and that's why the concentrated part is important. Because when you're hydrating, you want there to be plenty of water because you want to add water. So whether you're taking water away or adding water changes that reagent a little bit. All right, and then the second part, we need a peroxy acid here. So maybe something like peroxyacetic acid, or that other special one that we looked at called MCPBA. Either of those would work there. Did anybody come up with any other ideas or plans, or was there anything that you couldn't quite figure out about that last one that you want to talk about? Okay. Then let's take a look. So I want to be a little bit mindful of the time. Let's do one more and then move on to some new stuff. This one's going to be a little bit trickier. That's okay. Yes, Nicole, the peroxy acid makes it go into an epoxide. All right, give this one a try.
I know, but I still.
All right. So 3 steps. Yes, there's 3 steps. Yes. But that doesn't mean it's wrong to have more steps. Or maybe you came up with some super cool way to do it in 2 steps that I'm not thinking about. It's actually sort of like 4 steps, honestly, the way I'm thinking about it. Um, but 2 are kind of part of the same reaction. I wouldn't use PCC here, but you're on the right track, I think, for that last step. But think again about what exactly PCC does as opposed to other oxidants. All right, let's take a look at this. So, all right, so Nicole, I think you're on the right track with the thinking about what we do here. We have this carboxylic acid, so we have to make that somehow. And the way that we've been generally, or the only way that I think so far that we've seen to make carboxylic acids is by oxidizing alcohols. So we're going to start with an alcohol and then oxidize that alcohol to do this. And we'll talk about the specific reagents later. We just want to kind of get our plan first. So our first plan is to make this carboxylic acid by oxidizing an alcohol. All right. So then our next, whoops. I don't know if anybody noticed this. This is not possible. I left out a carbon here. So let's assume that carbon is still there. I'm sorry if that screws up your whole thing. Yes, Nicole, you're correct. We want to use chromic acid for that oxidation. But we can't just lose carbon. That's not a thing that we've known, so I'm sorry if that screwed you up. I forgot to leave that in. Oh wait, no. Sorry, out of it right now. We're not losing a carbon because 1, 2 carbons, 1, 2, 1, 2. I'm not paying attention. Okay. Sorry, let's think about that again. Okay, so yes, this is a chromic acid oxidation. Take a look at where we go from here. So we have this alcohol that's coming off of this terminal carbon, and we would like to put that here, but that kind of causes some issues here. We can't just do a substitution for the bromine because that's the wrong carbon. If we tried to substitute this, like do an SN1 substitution for OH, we'd be on the wrong carbon. So we have to. Is there some reaction where the OH can jump over a carbon over? Not really. Not from a tertiary to a primary carbon. So that tells us that that's not going to be a direct one-step thing. We can't just do something where the bromine substitutes and also jumps over. It's not going to work. So instead, we go back to this thing and we say, all right, well, if we can't get to this, what kinds of things can we make this from? So we could again think of this as coming from substitution. Could also be coming from hydration. So we could think about like having an alkene and then hydrating that. Yes, hydroboration oxidation would do that because we need that anti-Markovnikov, as we call it, selectivity, just the opposite selectivity. So that would work. So in this case, we've got two possible ways of making this alcohol. So that's when we start looking toward the beginning. That here, we've got something that we have to eventually make this stuff from. And making this alkyl bromide from this is really no easier than making this from. There's no reaction that says, okay, make the bromine jump over. I mean, there probably are, but not ones that we've talked about. To just sort of magically make that bromine jump over. So that's going to take some more steps and some more doing, and probably not a great way to do that this time. We're going to it's going to make more sense to do this because now I can see a really clear, direct path here through elimination. Does everybody see that? So we can eliminate from this bromine. Then we can add water through hydroboration oxidation, and then we can oxidize the alcohol to make the carboxylic acid. All right, so now let's add our reagents. And in this one, we have to be a little bit careful for a couple reasons. So one, as Nicole pointed out, we can't use PCC here because that would give us the aldehyde, and we want the carboxylic acid. So we want to use chromic acid. Now, as we talked about on Monday, chromic acid, even though that's the actual reagent that does the work, you can't like get a thing of chromic acid. So we generally use if we're specifying reagents, we would generally call this chromium 6 oxide, sulfuric acid, and water. So we're saying basically we're going to make chromic acid, but that's functionally the same thing. If you say chromic acid, I know what you mean, and that's fine. Over here, again, we want to add water, but we have to do it on this. We have to get the OH on this carbon, not this one. So that means we need hydroboration oxidation. So this is where it actually becomes like a 4-step thing because these are two distinct steps. And writing this down, I think our book doesn't put water in here specifically, but there's water in there. Okay, and then to finish this up, so first of all, let's just not confuse ourselves. So we decided this is not a great way to go. So to finish this up, here's where we have to be a little bit careful. There's lots of ways to do elimination, but like in the previous quiz, in quiz 8, yeah, there are different elimination products here. We could eliminate here, eliminate here. And in fact, this is really the favorite elimination product with most bases. So how do we make sure that we're eliminating only this way? Any ideas? What reagents do we have to put here to make sure that we're getting only this elimination? Any ideas? Nothing? Okay. So this is where we need a large base because we want to go to the less substituted product. So if we were to, just going to make some, yeah, so if we use something like NaOH, the problem with that is that that's more likely to form the more substituted elimination product, which is not quite what we want. Because we want this specific elimination product, we need a big base. If you go back and look in when we talked about E2 elimination, the only way to make the less substituted ones is to use a big base because then the steric concerns of like getting this big thing in there outweigh the stability issues that like this is actually the more stable thermodynamic product. We call those the kinetic control versus thermodynamic control. And bulk has too high of an activation energy to get into a crowded spot. And so it's going to preferentially grab the less crowded thing. So the big base, there are various ones that you can look up, big elimination bases. One that we've seen frequently is potassium tert-butoxide, which because it has this big tert-butyl group, is going to preferentially eliminate from the less sterically hindered spot, so the more open spot. Another way that that's sometimes written is as a reagent, this, so potassium tert-butoxide. That gives us the control that we need to make the less substituted alkene product, the kinetic product. All right, so that's a little tricky. Questions about that? Sorry, still waiting for it to save. Okay. So keep working on these. These are related to some ones in the back of the chapter. There are a whole bunch of transformations. If you can work your way through all of those, that's pretty much everything you will see at this point. And as we go on, we'll see more and more of them. But try to work them through as best you can without looking at answers, because as soon as you see answers, like when it kind of makes sense and it's obvious sometimes, but when you're working through it, as you saw, it's really not obvious and really difficult. So the best thing to do is to try it, write stuff down, and then come to me. Let's make an appointment to talk about it, bring it up in class if you can, and or send it to me so that I can see what you're doing and we can talk about what ideas work and what ideas don't work, as opposed to just looking at answers. Okay, let's move on. talk about aromatic compounds. So this is chapter 9. So aromatic compounds are not just things that smell, although that's originally where that name comes from. Aromatic refers to a particular structural feature where we have a ring with alternating double bonds with a specific number of electrons. We'll talk about what that is. So the most famous and most important aromatic compound, and the one that you can use to kind of think about this in general, is benzene. So this chapter is going to be all about the chemistry of stuff like this, of structures like this. So just to review, what's special about benzene? Well, maybe not to review, but to talk about some of the things we've seen before. We draw benzene like this: 6 carbons, 6 hydrogens, alternating double bonds. But there's also a resonance form in benzene, a resonance form of benzene that looks like this. And if we think all the way back to that chapter 1 or 2 when we talked about resonance, what that really means is not that this thing is flipping back and forth or that the electrons are spinning around the ring like that, but rather that the actual structure is an average of those two. So even though we draw benzene with 3 double bonds and 3 single bonds between the carbons, all the bonds are actually equivalent. And that's what originally led to the discovery of this structure, that if we had 3 double bonds and 3 single bonds, we would expect to see 3 short bonds and 3 long bonds, because single carbon-carbon bonds are longer than double carbon-carbon bonds. But instead, we have this perfectly symmetric structure. So what's really happening here is that those pi electrons are shared around all the carbons equivalently. And that's why we often see benzene actually drawn like this. So rather than drawing the individual double bonds, you sometimes see benzene depicted as a hexagon with a circle in the middle, which is showing all those shared electrons, that shared pi system. In organic chemistry, we usually draw it with the 3 double bonds like this, only because we're concerned about mechanisms. And so if we have those double bonds, then we can draw the arrows where the double bonds are, going out and doing stuff, and we're going to see some of those in this chapter. If we're only concerned about this thing as a structure, then we often see it like this. So if you look at like biochemistry type stuff, structures of larger biomolecules where they're not concerned about individual mechanisms, you'll often see benzene drawn like this. So what that means in terms of what's going on with the electrons in the orbitals, grab this picture from the book here. So the way that this is often shown this is a picture from the book, is something like this, where rather than thinking about each carbon here is sp2 hybridized, right? Everything is sp2. So that means you've got these 3 planar bonds and then 1 p orbital. And instead of thinking about this as each p orbital has 1 electron, what's really happening is the p orbitals have combined to make these molecular orbitals that are shared all the way around the ring. So you have this planar structure with these shared p orbitals, shared pi electrons, that makes this thing especially stable. So the reason that, or the way that we see this is especially stable, is that most alkene reactions, like from chapter, what was that, 5? Chapter 5. So, adding bromine, hydration, all that stuff. Most alkene reactions don't work on benzene because benzene is just too stable. So we saw reduction, like where you're trying to put hydrogen on there. You can reduce the rest of the chain, but you don't reduce the benzene unless you have a stronger catalyst. You try to add like bromine to benzene. Sorry, is my head in the way of this again? No reaction. You can't brominate those. So benzene's double bonds don't act as typical alkenes because of this special stability, which we call an aromatic stability. And there's some more examples in the book of where you can see like some specific energy values of how benzene is more stable and structures like benzene are more stable. You can look at those if you want. But basically, the conclusion of all that is benzene is especially stable, and that's why it needs its own chapter and its own reactions, because we can't just assume it behaves like other alkenes. It's special. Okay. So what is specifically this idea of aromaticity? When do structures have this particular stability and when do they not? So you need structures need to, or compounds need to satisfy these three requirements to have this special aromatic stability. So they have to have one 2p orbital, at least one 2p orbital on each atom in the ring. Okay, so that means that in the ring, whatever ring we're talking about here, everything has to be sp2 hybridized. So if we look at something like this, right, this would not be aromatic because this carbon here is sp3 hybridized and therefore does not have a 2p orbital. Okay, whereas something like this can have a 2p orbital because a lone pair can either be in a p orbital or in a hybrid orbital. So this one can work there. Condition, a planar or flat ring. All those p orbitals need to be lined up so that they can have that special stability. So have things like, I don't think of a good example here. very larger rings, for instance, that can't be flat and that have to kind of go like this, can't be aromatic. We probably won't see a lot of that. And then the third thing, and this is the kind of unusual one, they have to have a certain number of pi electrons. 18. And the formula for that is any number that fits 4n plus 2. So, 2 is 4n plus 2 when n is 0, 6 is 4n plus 2 when n is 1, and so forth. So you can just keep adding 4s there. You need that particular number of electrons in order to have the right molecular orbital filled for the stability of that. If you want to know more about that, we can talk about that, but it's a little bit beyond what we need to do for this class. So we can just say, let's just look for that count of electrons, and we're good. Where this gets a little bit tricky is, what do you consider pi electrons, and what do you consider not a part of that pi system, those p orbitals that are all pi bonding with each other? So, for example, let's start with benzene. We already know benzene fits these conditions because it's like the typical classic aromatic compound, but let's actually go through it. So first rule is, does benzene have one 2p orbital on each atom? Is it sp2 hybridized? So we go around and say yes, 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 yes. So we're good there. Second, is it a flat ring? Yes, everything is planar, it's flat. Generally, that sp2 hybridization thing is going to take care of that anyway. Third, does it have how many pi electrons? So pi electrons, we need to think about what that really means. Pi electrons are electrons that are part of pi bonds. That's easy to see when we're looking at double bonds. We see 2 electrons making this bond, 2 electrons making this bond, 2 electrons making this bond. So there's 2 pi electrons there, there, and there. And so 6 pi electrons total. And that is one of the magic 4n plus 2 numbers. So we would say, yes, this is aromatic. Okay. Let's look at another example. Cyclobutadiene. Cyclobutadiene, do we have one 2p orbital on each atom? So yes, 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 everything's sp2 hybridized. Is it a planar flat ring? Yes, it's flat because of the sp2 hybridization. And then we have to count up our pi electrons. So in this case, we've got 2 pi electrons from this double bond, 2 pi electrons from this double bond, and so that's 4 pi electrons. So no, this is not aromatic. And this is where it gets a little bit careful, because we think of benzene as like the typical aromatic compound, but not every ring with alternating double bonds is aromatic. And so this one is not, because it doesn't have the right number of electrons to have that special stability. So we would say this is not aromatic because it doesn't have the right number of electrons, and therefore it's not going to be especially stable the way that benzene is. Let's see how this applies then to what we call hetero cycles. Which are cyclic molecules with non-carbon atoms in them. So molecules that have oxygen or nitrogen in there. One of them is pyridine. That's called pyridine. Hetero cycles always have weird names. They don't have a real systematic naming convention. So we do the same thing. It kind of looks like benzene, but we have to check. So yes, it's all sp2 hybridized. It's flat, just like benzene. So then when we come to the electron counts, we got 2, 4, 6 pi electrons. But then the question is the lone pair included in the pi system or not? Is the lone pair part of those pi electrons or not? In this case, it's not, because nitrogen already has a pi bond here. So if we look at the hybridization, like if we look at this thing flat, like this, what we see is that we have our p orbitals on each carbon. From the sp2 hybridization, there's a hydrogen on each of these carbons too. And then, so that's our part of our pi system. And then we also see here on the nitrogen that same kind of thing. So we see that it's part of a double bond also. And that tells us that the lone pair must be in this extra sp2 orbital position like that. So we would say, yes, this has 6 pi electrons, 1, 2, 3, 4, 5, 6. Okay, so now let's look at a similar one. I think that'll be about it for today after this. This is called roll. And in this heterocycle, in this ring, we've got, hold on, sure. So there's that's a lone pair. So in this ring, again, the carbons are in the same situation. They're all sp2 hybridized. So that part is all planar and sp2. But we have to think about what's going on with this nitrogen, because if this is sp3 hybridized, then we don't have a flat system where everything has p orbitals. If it's sp2 hybridized, then we do. And this is where we break a little bit from what you might have learned in general chemistry. A lone pair can be in an sp3 or sp2. Whoops. Let's say it this way. A lone pair can be in a hybrid orbital or in a p orbital. So in general chemistry, we would have said, sorry, that's in my head. Yeah, I'll put that up. Okay. In general chemistry, we would have said, if I would have asked you to find the hybridization of this nitrogen, you would have said, oh, okay, well, it's got 4 groups. 1, 2, 3, 4. That makes it sp3 hybridized, and the lone pair takes up that sp3, one of those sp3 hybrid orbitals. But in fact, in these molecules, in organic molecules in general, if that can participate in resonance with the rest of the pi system, then that lone pair will actually take up a p orbital instead. So let's draw both of those so that you can see why it does. So if that nitrogen So I'm trying to kind of look at this on the side. So here's our p orbitals from the other double bond. So there's our pi system. So if the nitrogen were sp3 hybridized, then that means that the lone pair would be in a hybrid orbital, the hydrogen would be in a hybrid orbital, and everything would be tetrahedral geometry here. And therefore, that pi system could kind of go like this, but wouldn't actually make it all the way around the ring. Because that lone pair is in a hybrid orbital, it's not lined up properly. But what we're saying is, instead, when you have a lone pair, if it's energetically favorable to do so, that lone pair can actually, instead of being in a hybrid orbital, can actually take up a p orbital. So let me annotate this a little bit more. So in this case, we have an sp3 hybridized nitrogen, and the lone pair is not a part of the pi system. In this one, we have an sp2 hybridized nitrogen, and the lone pair is a part of that pi system. Because that increases the resonance stabilization, that's what the structure is going to do. Because now we can have that resonance all the way around the ring, and we get aromaticity. So think about rules with respect to parole. Are we all sp2 hybridized? Well, now, yes, we are. If we consider that lone pair being in a p orbital, we are. 2, are we planar? Yes. If that's sp2 hybridized, now we're all planar. 3, how many electrons do we have? Well, if that lone pair is not a part of the pi system, then we have 4 pi electrons, 2 from here and 2 from here. But if the lone pair is a part of the pi system, then we have 2, 4, 6, and then we're aromatic. So let's say we have 2 plus 2 from the 2 double bonds, from the carbon-carbon double bonds. We have another 2 from the nitrogen lone pair. Now we have 6 pi electrons, and now we're aromatic. So pyrrole is actually aromatic because of this, because that lone pair can take up a p orbital. It's not a sp3 hybrid orbital. All right. This is a little bit tricky. It's going to take a little bit of review, just because anytime we go back on something that you already learned, it's always hard to rewire your brain to get that. So, in general chemistry, it was lone pairs count, lone pairs count. They always count as a group, and you have to count them in the hybridization. And now we're saying, well, actually, they could go either way, and it's going to depend on the stability. All right. Okay, so that it is after 10:30, so I want to stop there. So next week, our exam is scheduled for next week, right? We haven't done a whole lot since the last exam. So, we talked about some alcohols and stuff. So I want to put that exam off, but I want you to have time to do it also. So what I'm thinking about is posting the exam up on next Wednesday, as it would be on the schedule, and then just having it open for longer, so that we can include this chapter that we're working on now, and you can kind of be working on the exam as we're going through the chapter and as we're practicing with the chapter. That way, I think it's better to just have more time with the exam than to just delay when I give it to you, and especially because of people's schedules and things like that. So so that's probably what we'll do. If you think that's a big problem, let me know. Otherwise, I'll see you next week. Just a couple other dates to keep aware of. So as usual, you can always email me for appointments for office hours. I'm also having open office hours Wednesday and Friday. Wednesday and Friday, 11 a.m. This is actually for everybody who's taking any chemistry class. I'm kind of like extra tutoring center type time. So if you know anybody who is trying to get help with chemistry and is having issues because of all the stuff, they can come to my WebEx room. I'll post a link. It's actually a separate link from the one that we use. I told the tutoring center to let people know also if people are looking for something, they can come see me. You're also welcome there, but you can always set up other times for more private work. Kimmy asks, for the final project, will we just not present them like we were going to before we switch to online? So yes, I would still really like you to present them, like if we could do it in this type of a session. If you have it on a computer, if you can connect with your computer and you can record yourself presenting it somehow. I know technologically and just time-wise, a lot of people can't make it to these morning sessions, so it probably won't be synchronous. But if you have any way that you can record yourself presenting your stuff, whether it's just audio and your slides or something, I think that would be really helpful. If not, then we'll just do a paper type thing. If you, I guess we want to make it fair to everybody. So those of you who are doing a project, I don't know, I'll have to think about it. I think we'll probably, maybe we'll just stick with the paper because I don't want to be unfair to people who don't have the capability of doing a presentation since we switched. So yeah, we'll probably not present them. I would like to find a way to do that. Maybe once I know for sure exactly how many people are doing the paper or the thing, we'll figure it out. But it may not be fair to require a presentation. So, asking. Other questions? Okay, well, let me know as your stuff comes up. Work through some of those synthesis problems, and if you could share some of your solutions, I would appreciate that, and I can give you some feedback on those. Otherwise, I will see you on Monday. And yeah, I hope the quiz 9 is going okay. Bye. Thanks. Do you have to know how to name thiols? No, I don't know. You don't have to know how to name thiols. No. Yep. Thanks.